Right, so this is lecture 4 out of 5. So in particular, if you just got here, I hope you brought something to read. All right. So, all right, we're at the heart of the matter. Again, we're just looking at Cm of Rn restricted to E, where E is finite. The last lecture will be somewhat redundant, not entirely redundant, with Aryeh's talk, passing from Cm to Sobolev spaces, where things are different. And I'm not going to be talking at all about the case where E is infinite, which was covered in Kevin Lully's talk. So, all right. But with those restrictions, here we go. This is the guts of the thing. I warn you in advance, I've tried to make it painless, but it isn't painless. And however, I promise you that the fifth and last of my lectures will be painless. Okay, so here we go. All right, let's remember yet again the notation. So X is now Cm of Rn, M and N are fixed. Here's the norm, yet again the Cm norm. Today, the jet of a function at X is the M minus first order Taylor polynomial of f at X. So it belongs to script P. Script P is the vector space of M minus first degree polynomials on Rn. Isn't this wonderfully clear? Thank you again, Paul. Okay. Let's see. Now, we're going to be interested in a set E contained in Rn. E is going to be finite for the serious stuff. So X of E is the set of restrictions to E of functions f in X, that is Cm functions. And so the norm of f in X of E is the inf of the norms of functions f belonging to the space X on the whole space that agree with little f on E. Okay? And remember the convention that whenever you see a constant denoted one way or another by the letter C, that always means a constant that depends only on little m and little n, that is, on which function space we're working in. So those are the standing conventions for God knows how many of these lectures, maybe all of them. Okay, so today we're dealing only with arbitrarily large finite sets E, not infinite sets. Okay, so in the first talk, there was the problem of deciding whether there exists a function f in X whose norm is less than a given m and agrees with data little f up to a multiple of a given tolerance sigma of X for all X in this large finite set E. And here f, sigma, E, and m are given. Okay, so I hope that no further review of that is needed. But again, I also hope that absolutely nobody finds anything unclear. So stop me if anything is unclear. Okay, well, the strategy in talk 1, mentioned also in talk, at least in talk 3, is that we define certain convex sets, gamma sub L of xm, contained in the vector space script P of all possible Taylor polynomials. They're defined for X in E. Actually, they're defined more generally than that, but never mind. X in E, M a positive number, L a non-negative integer, and they're defined by induction on L. Okay, in the base case, L equals 0, remember that gamma 0 of xm simply consists of all polynomials that do that, reflecting the fact that P is supposed to be the Taylor polynomial of a Cm function with norm at most capital M. And also that, reflecting the fact that our interpolant capital F is supposed to agree with little f to this accuracy. So again, this is the information, this gamma 0 contains the information that we get about possible Taylor polynomials P by just looking at the single point X and not looking at any other points. Okay? So that's the base case L equals 0. That's our gamma 0. And then remember the induction step. Fix L and fix M, and suppose that we have computed all of these guys for all X in E for the given L and the given M. Then we're going to compute gamma L plus 1 of xm. And not really, we'll use the oversimplified pedagogical algorithm. But here it is. So gamma L plus 1 consists of all P in the gamma L, such that for each Y in E, there is a P prime in the previously computed gamma L that has this degree of closeness to P that comes simply from Taylor's theorem. Okay. So that's the definition of the gamma L's. And the heart of the matter then is the following theorem. So the main theorem is that there are constants L star, a large enough integer, and capital C, a large enough real number, depending only on little m, little n, the parameters in the function space x, okay, for which the following holds. So take any interpolation problem of the kind that we've been talking about. So any finite set E, any real valued function f on E, any tolerance sigma, and any positive real number m. And suppose we're given such a problem, okay? Fix a point x0 in E. Just look at one point x0. If gamma L star of x0m is non-empty, then there exists an interpolant that has norm at most c times m and that agrees with the data up to c times m times the tolerance. So except for the fact that we've lost this factor of c, it means that we have been able to build an optimal solution provided simply that the gamma is not 0. Okay? More precisely, given P0 in gamma L star, we can find one of these nearly optimal interpolants whose Taylor polynomial at the given point x0 is equal to that P0. So morally, except for the fact that there's a constant c in these inequalities, except for that, morally, this thing consists precisely of the Taylor polynomials at x0 of interpolants that work with the given m. Okay? Is it clear? No objections. Okay. All right. So the proof of the main theorem is constructive, and with a little extra care, we can actually make capital F depend linearly on little f in the first version of the theorem, or on the little f and the P0 in gamma in the second version of the theorem. Okay. And in fact, it can even be, if you check very carefully and arrange things just right, it can be of bounded depth. And so the proof of this theorem gives a linear extension operator of bounded depth. And the consequence of that is that, as promised in the last talk, this theorem on the convex sets gamma of L implies the existence of a linear extension operator of bounded depth. And in the last talk, we reduced everything else to that. So it means that all the theorems that I've claimed, all 6 theorems, are now going to be proved thanks to the sketch of the proof of the main theorem. And I warn you that I really want to keep this simple. I don't want it to be technical and horrible, and the price of that is that I will lie to you. Okay? So for the truth, see the actual published papers which have been carefully checked. But for the spirit of the thing, and for God's sake, how many of you actually want to see the details of the proof? I don't want to consider that question. But for those of you who are content with the spirit of the thing, let's just accept the lies and go on. Okay, so I'm going to generalize the problem a little bit. There's going to be a local version of the problem. So in addition to the usual data E, F, sigma, and M, which mean the usual thing, okay, in addition to these guys, I'm going to specify a cube. And I'm going to specify a point x0, which belongs to E intersect 3q. It's convenient to dilate the cube a little bit by a factor of 3. Never mind. I'm lying to you anyway, so why am I careful about that? Well, all right, so we have a point x0 in E intersect 3q, and I have some jet p0 in P. Okay? And then the problem is to find a function f in x of 3q, the restriction of Cm to 3q, with the property that its norm is at most c times m, and it agrees with the data up to this factor, c times m, for all x for which the problem makes sense. In this case, not for all x in E, but for all x in E intersect 3q, because that's where capital F is defined. And furthermore, I demand that this capital F have this P0 as its jet at the point x0. So that's what I mean by a local interpolation problem. So on the one hand, we're only solving the problem locally on a cube q or maybe 3q, but we're demanding something a little extra, namely at a base point, we are prescribing the Taylor polynomial of our interpolant. So that's a local interpolation problem. Okay? All right. So let's give that a name. That's local interpolation problem, LIP, not Lipschitz, local interpolation problem of Q, X0, P0. Okay? So that's the local interpolation problem. And our main theorem simply says that we can solve a local interpolation problem when our cube Q is Q0, the unit cube, whenever P0 is in this gamma sub L star for a suitably large integer constant L star. That defines our interpolant only on the unit cube, but without loss of generality, we can take our set E to be contained in the middle half of the unit cube, and then it's trivial to modify it so to modify our interpolant so it's defined on all of Rn. Okay? So we will win if we can solve every local interpolation problem when this Q is the unit cube and when the P0 belongs to the appropriate gamma. So that's what we're going to do. Okay, in fact, we're going to prove that any local interpolation problem can be solved, provided only that the P0 belongs to the appropriate gamma. And remember, this gamma contains, so to speak, the true but unknowable gamma, and therefore, if P0 is not in this gamma, we have no chance of being able to solve the local interpolation problem. So this means that whenever the local interpolation problem is not simply ruled out by the fact that P0 fails to belong to the gamma, then in fact there is a solution and we can construct one. That's what we'll prove. Now, in order to prove that, we're going to measure the difficulty of a local interpolation problem by attaching to it a label, script A. So, okay. Okay, what is a label? Well, a label is just any, a label is just any subset of the set, fancy script M, of all multi-indices of order at most m minus 1, little m minus 1. Okay, that's what a label is. Now, labels are going to come with a total order relation that I just write like that, okay? So they come totally ordered, and roughly speaking, if one label is less than another, let's say if script A is less than script B, then we'll think that an interpolation problem carrying that label is easier than an interpolation problem that carries that label. Okay? So I haven't told you, well, I have told you what a label is. I haven't told you what the order relation is, and I haven't told you how labels get attached to problems, but hold on, that's coming. Okay? One property that I promise you of this order relation is that if remember these are sets of multi-indices, if script A is contained in script B, then script B is less than script A, according to this order relation. And therefore, any problem that carries that label is to be thought of as easier than that one. So in particular, everything contains the empty set, so the empty set labels the hardest problems. And on the other hand, every label is contained in script M, and therefore script M labels the easiest problems, the completely trivial ones. Okay, now to assign a label, script A, to a local interpolation problem, we look at the convex set gamma L of x0m, where this choice of L simply depends on the label. So this is an integer constant depending on the label, and we will arrange them conveniently. Okay? So the sets gamma had better have something to do with the way we construct functions f, because our hypothesis has to do with gammas being non-empty. And so here's how the gammas enter. So we're going to look at the size and shape of this gamma, and we're going to see whether there is room to maneuver inside gamma. And so in order to describe this, let me first suppose that P0 is inside the gamma, and if that weren't true, we have no business trying to solve the local interpolation problem. Again, this gamma contains the unknowable true gamma, and therefore, if P0 is not in here, we have no chance. So we're assuming that P0 belongs to this gamma. In that case, very roughly speaking, so now of all the various lies, I will tell you this is the biggest one. Okay, very roughly speaking, we attach a label script A to a local interpolation problem, provided not only is P0 in the gamma, but in fact P0 plus m times some P alpha also belong to the same gamma for each alpha in this set of multi-indices script A, where this P alpha is a monomial. It's a rescaled, so this is, remember, the diameter of or the side length of the cube to this appropriate power. But this is basically a monomial based at the point x. And let's see, I'm sorry, this is a typo. This is just y minus x to 0 to the alpha. This is an m minus alpha. This is an alpha. Okay. So, well, if a convex set contains not only this point, but all these other points, then sitting inside is a simplex of some kind, and so this thing contains room to maneuver. Okay? And again, I'm lying to you, but let's believe the lie for the moment, and in fact, for the whole lecture. Okay. Now, what are the main properties of labels? Well, let's see. Any local interpolation problem that carries the label A also carries the label B for any subset B. And that's obvious because the definition of carrying the label was that for every alpha, this thing belongs. So if you pass to a subset and there are fewer alphas, you're imposing fewer conditions. And so, of course, if this one is true, then the less stringent one is true. And so if B is a subset of A, then anything that carries the label A also carries the label B, which is why we should say that A is easier than B whenever B is a subset of A. Okay? Going once, going twice. All right. Now, every local interpolation problem carries the label empty set, because then our requirements are empty. For every alpha in the empty set, a certain polynomial belongs to gamma. Well, that's vacuously true. So only the most, all right, as promised, every local interpolation problem carries the label empty set, but only the most trivial ones carry the label script M. And I don't want to waste the 2 minutes to explain it, but the fact is that any local interpolation problem that carries the label script M is so trivial that maybe E intersect 3Q has only one point, or maybe something else, maybe the sigma is very big. But these problems are so trivial that we can take as our interpolant simply the given polynomial P0, and it's good enough. Okay, so problems with the label script M are trivial, and we can solve them by just taking our interpolant to be the polynomial P0. All right. Another crucial property of labels, which will not enter the discussion anytime soon, but which at some later point will save us from disaster, is that if we want to decide whether we can attach a given label to a local interpolation problem, it depends on the cube, it depends on the base point, it depends on the set E, it depends on all kinds of stuff, but it does not depend on this polynomial P0. That's a crucial point, and we'll see that coming back. Okay, and if you just remember the definition of how we attach the label, the polynomial, actually the polynomial P0 does appear, and so it's not immediately clear why this should be true. It has to do with some of the lies I've told you, but in fact, this statement is in fact exactly true, and it only appears to be false because it contradicts a previously asserted lie. Okay. All right. All right. Now, we're going to use labels to prove the main theorem. And the idea is that for each label, there is a strategy as to how to construct an extension, capital F. And these strategies get more and more complicated as the labels get harder. And we will proceed by induction on the difficulty of the label. So we are going to work by induction on the label with respect to this order relation, and we will prove for each label a main lemma for script A. Here's what it says. The main lemma for script A says, take any local interpolation problem, suppose that the P0 belongs to that gamma. Again, the L is determined by the label A. Okay? And suppose that this problem carries the label A. Then the problem has a solution. That's the main lemma. So that had better be true, or else there's no solution. And we're working by induction on script A, and so we assume this carries the label script A. And under that assumption, our local interpolation problem has a solution. That's the statement of the main lemma for A. Now, every local interpolation problem carries the label empty set, and therefore the main lemma for empty set says that for any local interpolation problem for which P0 is in the gamma, here I've put empty set for A, this can be solved. Aha, that's what we wanted to know. And so the main lemma for script A equals empty set implies the main theorem. So we really only need to know the main lemma for the empty set, but that's the hardest case, and we're going to proceed by induction on the label A. Onward. Okay, so proof of the main lemma for A by induction on A. Well, first comes the base case. Now, the base case is trivial. Remember that if a local interpolation problem carries the label script M, then it's enough just to take capital F equals P0 and it works. So all we have to do is check that it works. Well, we're not going to, but trust me, it's easy. And so that's the base case. And so in particular, one can take this L, this integer depending on the label, and when the label is the most trivial one, script M, we declare that the L is equal to 1. And so we then have to check that if P0 is in there, then it follows that this interpolant solves the interpolation problem. Okay, and it does. So that's the base case. Now we've got to do the induction step. Let's see how much time I have. Lots of time. Okay, so for the induction step, we fix a label script A other than the base case, so it's not script M, and we assume that the main lemma holds for all labels less than script A, and then we're going to prove the main lemma for script A. And if we can do that, we've accomplished the induction, proven the main lemma, proven the main theorem, and proven the 6 theorems from the last talk. Okay, and there indeed. So all we have to do is this induction step. Okay, now there are 2 cases for the proof of the induction step. This label script A, for which we need to establish the induction step, is either monotonic or non-monotonic, and in a minute I'll tell you what that means. Okay, the monotonic case is the serious case where we're going to have to do something. The non-monotonic case is a trivial case where we have to do almost nothing. So let me start explaining that, maybe starting with what does monotonic mean. So remember, script A is a set of multi-indices of order at most little m minus 1. So I'm going to call this monotonic if this condition holds. So suppose that I have alpha in script A, and then I add another multi-index to it. I want that sum to belong to script A. Well, of course, that's utterly ridiculous unless the sum is of order at most m minus 1, because script A is a set of multi-indices of order less than or equal to m minus 1. Okay? But so script A is monotonic if alpha in A and alpha plus beta of order at most m plus 1, or m minus 1, excuse me, implies that the sum alpha plus beta is in script A. What the hell does that have to do with anything? Anyway, that's what it means for script A to be monotonic, and so script A is either monotonic or not. All right. Now, let me try to explain why the non-monotonic case is essentially trivial. So here's the observation. Look at the blue writing. So suppose G is a CM function with norm at most 1, and furthermore, suppose it's close to 0 on the set E. It's within the tolerance sigma of x for all x in E. And suppose that the jet of this G at the base point x0 is equal to the monomial y goes to y minus x0 to the alpha. Okay? Well, if that's true, then basically you can just multiply G by absolute x minus x0 to the beta. Well, that's a polynomial that's bounded for x near x0. We have the slight embarrassment that as x gets far away from x0, this gets big. So let's take a harmless cutoff supported in a ball of radius 1 about x0, but let's say equal to 1 in a smaller ball of radius 1/2 maybe about x0. And then we simply take g tilde to be the harmless cutoff times x minus x0 to the beta times g of x for all x. And let's assume that this beta is such that alpha plus beta is less than or equal to m minus 1. Okay? So here's a g which is sort of harmless from the point of view of our interpolation problem. it doesn't, I mean, adding G doesn't change. I mean, if F works, then F plus mg will also work. And if F is within m sigmas, then F plus mg is within m plus 1 sigmas. Okay, this represents, the existence of such a G represents freedom of maneuver within the set gamma. And so if we have the freedom to maneuver by adding G, we have also the freedom to maneuver by adding G tilde. And so the G tilde is, I mean, what this slide is trying to say is that G tilde is just like G, except that alpha is replaced by alpha plus beta. And what that means is that if script A is a non-monotonic label, then by definition we can find an alpha and a beta with alpha plus beta in script M minus A. And if you do bookkeeping, you discover that any local interpolation problem that carries the label script A also carries the label script B, which is script A union alpha plus beta. You can add this one more multi-index to the collection A, and any problem that carried that label A also carries that label B. And I'm sorry, I have a feeling that wasn't quite clear. Brevity is the soul of wit. Let's go on. Consequently, the main lemma for script A follows from the main lemma for script B, right? Any interpolation problem that carries the label script B can be solved. Well, any interpolation problem that carries the label script A carries the label for also the label script B and can therefore be solved. B is less than A because A is a subset of B. So we're assuming by our induction hypothesis, any label less than A is already dealt with, and so the main lemma for B is already known, and so the main lemma for A follows. So non-monotonic sets are trivial because of that hand-waving argument. Okay, so the serious case is, right, so as promised, the induction step is essentially trivial in the non-monotonic case, and so now we're going to do our serious work in the monotonic case. Okay, so let's remember what we're doing. So we fixed a label script A other than M, and we're assuming now that it's monotonic. We're assuming that the main lemma holds for all labels strictly less than A, and we now fix a particular local interpolation problem which carries the label A, but let's say does not carry any label script B smaller than A, because if it did, we would already be able to solve it by the induction hypothesis. Okay? And now what are we supposed to do? Well, we're assuming that for this problem, we're assuming that P0 is contained in gamma sub L of A of X0M. And under these circumstances, the main lemma for script A tells us that we can solve this local interpolation problem, so we've got to do it. We've got to find a solution to lip 0. And if we can do that, then we've proven all the results claimed. Okay, so that's what we've got to do. All right, the plan. So I think I'll go through this plan 3 times, once very high level from 30,000 feet, once not quite so high level, and then once with more detail. Okay, so what we're going to do is that we're going to use a Calderon-Zigmund decomposition. We're going to cut 3Q0 into Calderon-Zigmund subcubes, Q nu. We're going to use the inductive assumption, that is, we're going to use labels less than script A to solve a local interpolation problem on each of these 3Q nu. So now the world 3Q0 is cut up into, let's say, Q nu, therefore covered by 3Q nu. And on each 3Q nu, we have a local interpolant obtained by solving a problem that we already know how to do because it carries an easier label. And then we're simply going to patch those local interpolants together using a partition of unity. That's the 30,000 feet description. Okay, here it goes. So now from, I don't know, from 100 feet. Okay, so step 1, we make a Calderon-Zigmund decomposition of 3Q0 into finitely many subcubes Q nu. Nu equals 1 to nu max. So remember, remember that to make a Calderon-Zigmund decomposition, we have to specify a rule. Okay? Given a cube, we either like it or don't like it. And it's up to us to say what it means for us to like it. But once we say that, then we look at it, we take our big cube, let's say 3Q0, and we decide, do we like it? Ah, yes, we like it. Okay, then we keep it. But if we don't like it, we bisect it. And then we look at each of the bisected cubes and we ask, do we like them? And any that we like, we keep. And any that we don't like, we bisect again. And so on and so on and so on. And so we keep on bisecting until we reach cubes that we like. And in this particular Calderon-Zigmund rule, we will discover that any sufficiently small cube Q is a cube that we like. And therefore, the procedure eventually stops, and we will partition 3Q0 into finitely many subcubes. So that's step one. Show picture on page 55. Well, let's skip that. Let's skip that picture for a minute, but there will be a picture on page 57. Then I'll need to ask your help. Thanks. Okay. All right. Now, step two. For each of these Calderon-Zigmund cubes, Q nu. Well, so let's see what's happening. Let's look at E intersect 3Q nu. It might actually be empty, in which case our local interpolation problem is to construct a function capital F, a local interpolant, that agrees with a given function on the empty set. We should be able to do that. Okay? So the non-trivial case is to look at a Calderon-Zigmund cube Q nu such that E intersect 3Q nu is non-empty. And in that case, we're going to pick a point, x nu, in there, and we're going to pick a p nu in there. Okay? Once we've done that, we will consider the local interpolation problem sub nu, the nuth problem, in which we change, instead of having the original cube Q0, we will now have this smaller Calderon-Zigmund cube Q naught, and in place of the base point x0, we'll have the base point we picked x sub nu, and in place of the original polynomial p0, we'll have this p that we picked, p nu. And so now we will have a local interpolation problem to consider. Show picture on page 57. Okay, let's get the picture on page 57. Okay, so notice in black we have the big cube Q0, and we have a base point. Where am I? There's this big guy is Q0. There's our base point x0, and attached to that there's also a polynomial p0, and we're trying to make the jet of our interpolant equal to p0 at that base point. But we've cut the world up into Calderon-Zigmund cubes, and I've shown 3 of them. And for each of these Calderon-Zigmund cubes, we've picked out a base point, and we've picked out a polynomial. So for the cube Q mu, we've picked out that guy. For the cube Q nu here, we've picked out these guys. For the cube Q nu prime, we've picked out these guys. Okay? So for each one of these, we have a local interpolation problem, and we will try to solve it. Okay, let's see. How can I toggle? Oh, congratulations. All right, I'm afraid I'll want this picture back in a few minutes. Get a little bit of exercise. Okay. Okay. Now, the step 3, the Calderon-Zigmund decomposition from step 1 is defined with a very important property. It is defined to guarantee that each one of those local interpolation problems carries a label, maybe different labels may be for different cubes, but nevertheless, each one of those cubes carries a label strictly less than script A. And therefore, by the induction assumption, we will be able to solve the nuth local interpolation problem from step 2. So we've taken one local interpolation problem on a big cube Q0, and we've cut it into a lot of little interpolation problems on smaller cubes Q nu, and we can solve each of the local problems. Okay, thanks to the induction hypothesis. Okay, well, so for each Q nu, at least for each non-trivial one, right, for which we're not trying to interpolate on the empty set, let's say F nu is the solution of our local problem. So this is our local interpolant. How about if 3q nu intersect D is empty? Well, then we don't have to worry about our interpolant agreeing with F on E, obviously, but we do have to worry about our local interpolant agreeing well with the given polynomial P0 at the base point. So a clever thing to do is just to put F nu equal to P0 at that point. Remember, we started with the interpolation problem lip 0, and it had a polynomial P0. That's the one I mean. Okay? So now we've defined for each Calderon-Zigmund cube Q nu a local interpolant F sub nu. That's step 4. And so now, okay, so for each Q nu, we found a local interpolant, and it does this good stuff. These are our local interpolants. We will patch them together. To patch them together, we simply use a partition of unity constructed in the same way as in Whitney's 1934 proof. Once we have a Calderon-Zigmund decomposition with reasonable geometrical properties, we automatically get from it a partition of unity that does this stuff. Okay? And so we use that same partition of unity, and we then simply define our interpolant F to be the patched together function made from the local interpolants F nu and patching by means of the partition of unity theta nu. That's our F, and we hope it works. Well, does it have a chance? Can it work? Well, we are facing the same problem that Whitney faced in 1934, which is that we're gluing together a lot of functions F nu, each of which may look perfectly all right, but we're gluing them together with a partition of unity theta nu, each of which lives on a little tiny length scale, or many of which live on a little tiny length scale. Okay? Therefore, the derivatives of the theta nu are enormous. And so there is the risk that because these derivatives are typically huge, that these derivatives may be huge. That's not quite what we had in mind. Okay, as in the proof of Whitney's theorem, a clever thing to do is to look at each particular Q nu hat and to write F this way. This guy is, with any luck, harmless. And now, instead of theta nu multiplying an F, which is not necessarily small, it's multiplying the difference of two F's, which might be very small. And so we hope that these derivatives, that the derivatives of this function are small whenever Q nu and Q nu prime touch. Okay? If that happens, these derivatives are big, but these derivatives are small, and we've got a chance that, therefore, the derivatives of these guys are medium-sized, and in fact, that will happen. Okay? So now remember, remember F nu has solved a local interpolation problem, so in fact, we know its jet at one point, namely x nu. And F nu hat, similarly, has been picked to solve a local interpolation problem, so we know its jet also at one point. So to say that the derivatives of F nu minus F nu hat are small amounts to saying this whenever Q nu and Q nu hat touch. Okay? So remember, to each Q nu we associated a polynomial P nu, and then to the neighboring Q nu hat we therefore also imputed a P nu hat, and these have got to be close together in the sense of these estimates. If this cube is very small, these guys have got to be very close. Maybe, pardon me, I'd like the picture on page 57 back again. Thanks. Okay, and in just a minute we'll get back to the text. Okay, so notice here are two cubes. Think of them as being very tiny, although I drew them sort of medium-sized. Think of them as being very tiny. We had an x nu here and a p nu here and an x nu prime and a p nu prime here. And what has to happen is that, remember, what we did was we looked at q nu and we said, okay, I have to pick an x nu and a p nu. And then we looked at q nu prime and said, okay, I have to pick an x nu prime and a p nu prime. These have to be picked in such a way that the derivatives of that minus that are small, where the definition of small has to do with the diameters of these cubes. So we've got to attain mutual consistency. That guy has to be close to that guy, close enough to that guy in a suitable sense, and that means that we're in grave danger of being unable to pick the p nu independently. The p nu have to be picked in such a way that they're related to one another, or else we have no chance. Okay, so picking a lot of p nu with the correct relationship to one another is very different from looking at each cube separately and picking a p nu. And so that's bad news for the induction. I'm sorry, was that a question?
Is that 3Q0?
Yes, it's really 3Q0, but compared to the other lies, that's nothing. But you're quite right. Okay, so let's get back to the text. Thanks. Thank you. All right, so let's say that this estimate means that these p nu, this collection of p nu, is mutually consistent. The p nu are mutually consistent, and we not only have to pick p nu, but we have to pick them mutually consistent. Okay, so there we go. How are we going to do that? Well, from 100 feet, we can't tell, but now comes the more detailed version. I have 7 minutes. Okay, let's do it. Carrying out the plan. Okay, step 1, the Calderon-Zigmund decomposition. Given a cube, Q, either we like it and keep it, or we dislike it and bisect it according to the following rule. So now here comes our Calderon-Zigmund rule. Okay, we like and keep Q if one of two things happens. Either E intersect 3Q has at most 1 point, or for some x in E intersect 3Q, the local interpolation problem LIP of QX capital P carries some label less than script A. Okay? That's the definition of the rule. Now, does this rule even make sense? Is it well defined? Notice I've told you what Q is. Q is the cube we're thinking about. We want to decide whether we like it. And we say for some x in E intersect 3Q, this happens, so we know what x is. But what is this P? What the hell is P? I haven't told you yet what P is. We haven't picked P, but it doesn't matter. Remember, when we decide whether a local interpolation problem carries a given label, it doesn't matter what P is. That's why we need that property.
Well, it does matter within some constraints, because if P is huge, you will not be able to achieve the estimate.
Yes. So, yes, all right. But this conversation is veering dangerously close to forcing me to tell the truth, which I don't want to do. Okay. So, all right. That is our rule. Notice that whenever we like a cube Q, either E intersect 3Q has at most 1 point, and therefore in our local interpolation problem, we will be trying to interpolate a function defined at 1 point. We're fully capable of doing that, okay? Or maybe no points at all. That's even easier. Or for some x in here, we are obtaining a local problem with a label script A, less than script A. That's great. That's what we want. We love problems with labels less than script A because we know how to solve them by induction hypothesis. Okay, so that's the Calderon-Zigmund rule, and it behaves as promised. So now we get a decomposition of our unit cube, or of our big cube Q0, and it behaves as promised. Okay, how about step 2? Well, so all right, let Q nu be a Calderon-Zigmund cube. We have to pick a point here, unless of course this intersection is empty, and then we have to pick a P nu in here. And I've said something about picking the X nu, but so far I haven't said anything about picking the P nu. Well, all right, Q nu is a Calderon-Zigmund cube, so we like it, but we don't like its parent. Let's not worry about its parent just at the moment, but we like it. So that means that either that happens, that means our local interpolation problem is trivial, or in the serious case, this guy carries a label script A for some x nu in there. So, all right, in case A, the local problem is trivial, and in case B, at least we found our x nu. We may not have found our P, but we found our x nu. There it is. All right, fine, but now how do we find our P? Well, in the non-trivial case, oh my God, boy, these slides keep beating around the bush. All right, we found our x nu. Now we have to find the p nu. Well, remember the definition of the gammas. The gammas were defined by an induction on this index L. By definition, if p is in gamma L plus 1 of xm, and y is any other point in E, then there exists a p prime in the gamma L of ym, which is close to p in the sense of these familiar-looking estimates. So there exists such a thing. And we've got already our p0, right? We have already, by hypothesis, a p0 in gamma sub L of A of the base point x0m, and we have our point x nu, that's the base point for the Knuth local interpolation problem, and so by the inductive definition of the gammas, there exists a p nu in this gamma such that all this stuff holds. Aha, we've got ourselves a p nu, and it belongs to a gamma. Isn't that wonderful? Might we possibly simply use that p nu and declare that it's what we want? Unfortunately not. Remember that this gamma has room to maneuver. We like the cube, so the gamma that means in particular that gamma carries some label, and that means that it has room to maneuver. And the fact that it has room to maneuver means that we can change our polynomial p nu. It isn't uniquely specified or anything like it. We have a fair amount of arbitrariness in picking it. And therefore, if we look at two adjacent Calderon-Zigmund cubes, we might pick two very different polynomials p nu. And so each one looks perfectly all right, but they're not mutually consistent, and we have no chance. So this is not good enough. And so we have to do something else to maintain the mutual consistency of the p nu. And so the happy surprise, the happy surprise for those of us struggling to prove the theorem is that there's a very simple thing we can do. Namely, we can pick our p nu in this previous gamma, in gamma L of A minus 1, that satisfies these same estimates as before, but also has this crucial property that if we look at p nu minus p0 and we take alpha derivatives of it, for any multi-index alpha in this set script A, this will be identically 0. That's an extra consistency condition. Now I have, oh my God, how many minutes? I have 1 minute left to go. Oh dear. All right. This is possible because there's room to maneuver and because the script A is monotonic, and certainly in the 45 remaining seconds I can't explain that to you. Okay? But it is possible not only to pick the p prime in the gamma as explained, but also to pick the p prime in the gamma in such a way that some extra derivatives of p nu minus p are identically 0. So that's possible again because there's room to maneuver and because script A is monotonic. Okay? The mutual consistency of the p nus will now hold because there isn't too much room to maneuver. And the reason there isn't too much room to maneuver is that we didn't like the parents of our Calderon-Zigmund cubes. I don't have time to explain that. Understanding all that is the hardest part of the proof. Let's just declare victory and say that we have accomplished step 2 of the plan and achieved the mutual consistency. So I've skipped over the hardest part of the proof, but that's the motivation of the hardest part of the proof. Okay, and so now we've looked separately at each q nu to pick a p nu. We've made an independent choice on each p nu, and yet our choices are somehow magically mutually consistent. That's the beauty of picking the Calderon-Zigmund rule the way we did. And so now, as promised, except in trivial cases, we've carried out steps 1 and 2 to guarantee that all the local interpolation problems are either trivial or carry labels less than script A. Therefore, we can solve each local interpolation problem and obtain local interpolants. That takes care of step 3 of the above plan. Step 4 of the above plan is just to introduce the Whitney partition of unity related to this Calderon-Zigmund decomposition. We can do that the same way Whitney did it in 1934, just using a different set of cubes. Step 5 was to patch everything together. Well, there's the formula. It makes perfect sense now that the theta nu and the f nu are well defined. And we're done with step 5, and now we simply hope that it works. We have carried out all of these steps and guaranteed the required mutual consistency, and it works. And that's the proof. This concludes the proof of the main theorem. We got through it. Okay, this was the most technical of the lectures. And I promise you that the next and my last, not the last, my last talk of this series, I hope it won't be my last talk, will be much easier. Thank you very much. Bye-bye. So L star depends, so, okay. All right. All right, so let's say just from the point of view of the statement of the theorem without worrying at all about the proof, L star depends only on little m and little n, where our function space is C little m of R little n. So how many derivatives do we demand and what dimension are we in? That's what L star depends on. Okay. From the point of view of what happens inside the proof, there are these labels script L of, there are these labels L of script A. And what we need to do is to make that proof work. Remember, we passed from L of A to L of A minus 1. We've got to make sure that L of A minus 1 is greater than L of B for any B less than A. So you might think, all right, L of A is, let's say, something like the number of labels less than A. Actually, because of some of the lies I've told you, it turns out that L of A has to be something like 1 plus 3 times the number of labels less than A. Okay? And since labels depend only on what dimension we're in and how many times we differentiate, that's some constant that you can calculate. And then finally, the L star in the statement of the theorem is the L of the label A, where you take A to be the empty set.